In the previous lecture, mostly we were dealing with the paraxial theory applied to the thin spherical lenses. And so we were basically assuming that the lenses were thin and that this simple theory was enough for their analysis. So as we start to look at an optical system with more detail, we'll find that although that's good enough for a first rough solution, we need to take it a little bit further. So we will be looking at the compound lens systems in different instruments such as telescopes and microscopes. We'll be looking at thick lenses and mirrors. Next week we'll be looking at aberrations. So our double lens system. I'm not trying to help you here to become proficient in designing modern lenses in this way, but I just want you to become familiar with a way that you can use and adapt lens systems that are already available. So I've sketched out a rough arrangement, and these are the approximate calculations that you do before you start doing the refined lens design. Those final lens design calculations, of course, carried out by computer. So we have here two thin positive lenses. They're separated by a distance between them. We can locate the position of the image that is formed first of all by lens 1. So if we look at a point of the object and light rays coming from that, they will travel over to lens number 1 and they will be bent. If we ignore lens number 2 for now, then these light rays will continue along their merry way until they reach, well, actually they will keep on going forever, but they will converge somewhere out here, and that point of convergence is going to be the point on the corresponding point on the image. So we know how to work out this distance here from the lens out to our real image. We'll call that I1. Now, clearly the rays that we've traced on the left of the lens are real and physical, and the ones in between the lenses are real and physical. But as soon as we pop in lens number 2, then these rays no longer exist. So what's going on? What we're going to do is we are going to treat this image as an object. And the reason we do that is because you'll remember that an image distance I is essentially a shorthand for saying where the rays converge. So I is just a mathematical way of indicating where the rays are converging. And we do have converging rays arriving at lens number 2. Lens number 2 sees them converging and behaving as though they're going to cross some distance over here. So what we can do then is we can measure the distance from the second lens out to where the image would be, and we will call this real image now an object. Okay, so putting an object over here is our mathematical way of saying that we have converging rays arriving at lens 2. And it's virtual, isn't it? Because it's on the right-hand side of lens 2. So we use that virtual object distance and we can find out our new image distance that is formed by the second lens, I2. and there's our final image formed right there. To find the magnification is actually quite straightforward. We look at the magnification that is caused by the first lens, so that gives us the ratio of the first real image height compared to the object height, and then we look at the magnification that is caused by the second lens, so we look at our second image height compared to our second object height. Simply multiplying those two magnification gives us the total magnification of the final image compared to the original object. So here is an example of the ocular or the eyepiece, and we're going to be using this lens in a couple of compound lens systems shortly. So this is essentially a magnifier, except we're not viewing an actual object with this when it's behaving as an eyepiece. We are in fact looking at an intermediate image of an object. So this is an intermediate image of an object that is somewhere else. A previous lens system has formed this image. So when we are looking into the eyepiece is looking into the optical system. And the eyepiece is providing a virtual image for us of this intermediate image. The virtual image is often out at infinity, or sometimes it's at the near point, 250 millimeters away from the eye. And as before, the angular magnification is given by the ratio of the focal length and the near point, 250 millimeters. So this two-lens system is known as the telescope. In fact, it's the astronomical telescope. So its function is to enlarge the image of on the retina of a distant object. In this case, the object is infinitely far away. So a real intermediate image is formed at the focal point. This image is the object for the next lens system, and in this case it's the eyepiece. So the role of the eyepiece is to form a virtual magnified image. In this case you can see the magnification is a magnification in angle. The angle made between these rays and the optical axis is larger than the angle of the original rays and the optical axis. So an astronomical system like this is known as an afocal imaging system, and that's because the conjugates are infinite. So we have infinite object distance and infinite image distance. If you were to shine a laser beam in here with parallel rays, it would emerge still collimated. However, the cross-section would be different. The magnification is worked out by using geometry. So that gives us a magnification that is the ratio of the objective focal length and the eyepiece focal length. The negative sign indicates that the image is upside down compared to the object. So now we are looking at the compound microscope. This is a simple version, and it's actually conceptually the same as the rather more complicated ones you'd see in a modern laboratory. However, this basic design is roughly 400 years old. The lens system here, it's a single lens that's closest to the object, is called the objective. It forms a real and inverted magnified image of the object. Now, rays diverge from this point here, and they then will hit the eyepiece and they will come off parallel to each other. So this eyepiece here magnifies the image even further. The magnification of the total system is the product of the transverse magnification of the objective. So that is, how much is this intermediate image larger than the original object, M object here, and the angular magnification of the eyepiece, which as we know is 250 mil divided by the focal length of the eyepiece. A thick lens is one where we can no longer neglect the thickness of it. We can't any longer use the Gaussian lens formula of 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. Thick lenses still have primary and secondary focal lengths, so let's see how we can use the understanding we have of primary and secondary focal lengths and use the trick of principal planes to simplify how light rays travel in a system like this. So here is our on-axis object. It's going to be located at, let's make that a 1 at the primary focal point. So light rays from this will propagate outwards. And what we're going to do is we are going to pretend we're going to propagate them all the way to the front of the lens and then keep going until we reach this thing called the first principal plane. Then what we do is we hop from that intersection there with the first principal plane to the second principal plane, and we say, well, because our light is coming from the primary focal point, everything out here is going to be propagating parallel with the optical axis. So the red rays outside the lens are at least physically correct. The red rays inside the thick lens are just useful mathematical tricks. Of course, in actual fact, the ray is going to be bent at the front of the lens. It'll propagate in a straight line until it reaches the second interface where it bends again. So the physical rays inside the lens are actually more like those yellow ones that I've drawn. But the trick of using principal planes means that we can assume that the thick lens is actually a thin lens, which is divided in two. The front half is located at H1 and the second half is located at H2. To calculate where those principal planes are located, we need to know the thickness of the lens, D. We need to know the refractive index, the radii of curvature, and we need to know here the effective focal length. So this is the effective focal length of the thick lens, and we'll see shortly how do we calculate that. To just clarify our sign convention, we are going to assume that all H's are right, are positive to the right. So this is the front vertex is the origin for H1, and the second vertex is the origin for H2. But both of them are positive towards the right. So here is how we calculate our effective focal length. At first glance, you can see it looks very similar to the focal length of a thin lens, but we have an extra term here. And of course, as you'd expect, this extra term has got the lens thickness in it. So in this tutorial problem, you'll look at an equiconvex lens with a certain refractive index and radii of curvature, R1, R2, and N, and you're given the thickness, which is very important. Let's call it D here. We've got an object placed 10 mil over, this should read the left of the lens. So your job is to find the effective focal length and the power of that lens. Then compare that to a thin lens with the same radii of curvature. In other words, a lens where thickness is equal to 0. Then find the distance of the vertices to the principal planes, H1, H2. Draw a scale diagram of it and find the image, the magnification, and the angular magnification. We can also treat a compound lens in this same thick lens way. So we can find the effective focal length of a combination of lenses. So we might have a lens here with focal length f1 and another lens here with focal length f2. We can find an effective focal length of the whole combination. The important parameter now is the distance between those lenses. And we use slightly different formula to find the principal planes, but what these principal planes are in their nature is the same as before. If I use a slightly different color and find that we measure the position of H1 from the first lens, some distance to the right, H1, and H2 is similarly measured from the center of lens 2. So in this question, we've got two thin lenses with focal length number 1 and focal length f2. We've given the distance between them. We need to find the effective focal length, the effective power, and the distances from the lens centers to the principal points. So we need to find H1 and H2. And then do a sketch of the system and show where the principal planes are located. Principal planes, incidentally, don't necessarily have to be both inside the lenses. You may have them both on one side, both on the other side. They might even be back to front. So in this case, I am not going to give you a hint of where they're located. You need to find out where they are. And I also want you to find the focal points F1 and F2. Now, I'm sure any of you realize that the average camera or microscope or telescope you've seen is way more than just 1 or 2 lenses. they have incredibly complicated combinations of lenses. A microscope objective, for example, may be a really cleverly engineered design and may cost hundreds or even thousands of dollars just for that objective lens. Nevertheless, we can find a system of principal planes, H1 and H2, and we can find an effective focal length, no matter how complicated the system. So these are really useful parameters to have, because then you can, in your head, do calculations for where image distances and object distances are located using our favorite Gaussian lens formula. The way that we use that is by measuring the distance from the object not to the lens but to the first principal plane, and we measure the distance from the second principal plane to the image rather than from any particular physical feature in the lens. Now, it would probably take a skilled person 10 or 15 minutes just to find the trajectory of a single ray through a complicated system like this. But a computer could do it in a millisecond, so we don't need to always do things by hand. So how do we set this problem up so that a computer can do it? Let's look at what one particular ray from the tip of this object does. The first thing it does is it translates to the part of the lens. There, it refracts. It translates to the back of the lens, refracts again. And there being nothing between there and the next lens, we see another translation. At every interface, of course, we have another refraction event, and in between those refraction events, we have simply translation taking place. So the repetitive manner by which the light goes through these transfer and refraction processes is something that we can mathematically do using matrix operators. What we're going to do is we're going to consider a ray as a vector, a two-dimensional vector. You can consider them three-dimensional, but I think that it's quite instructive just to look at it in 2D for now. Y1 is going to be the vertical distance from the optical axis, and theta 1 is going to be the angle above the optical axis. So let's say our ray starts from here and then it moves along over a distance d. Clearly, there's no refraction has taken place, there's no interface, it's just moved along. So this angle is not going to change, it's going to remain theta 1. However, the height, y2, is going to be different. It's no longer going to be the same as y1. We'll use trigonometry to work out what the new y2 is. So this is how we follow the ray from position 1 through to position 2. We can construct a little triangle here and work out how large the size is. Obviously, we'll be using tan of theta 1. Since we're using the paraxial approximation, then we know that tan theta is approximately equal to theta, and we're not going to use the higher order terms. Higher order terms are negligible. So that gives us an expression down here. y2 is going to be theta 1 times d, where d is the distance it's travelled along the optical axis, plus y1, the height at which it started. Okay, so now we have two equations. One is the vertical position of the ray after translation, and one is the angle of the ray after translation, which is, as we said before, simply theta 1. But I've written this 0 in here, 0 times y1, for a reason. And that is because we can recast these equations in matrix form. So we've started off here with our original ray vector, y1, theta 1. We multiply it by this translation matrix, so you can see that the 1 and the d here come from the 1 and the d in this equation, and the 0 and 1 here come from the 0 and the 1 in the equation for theta 2. So this matrix in the middle is our translation matrix. Sometimes we give it the symbol T. In the case of refraction at a vertical interface, when the refraction takes place, there's no horizontal translation. So I'll just put d equals 0 to remind you. And in that case, the vertical position doesn't change. So y2 is equal to y1. The thing that does change is the angle. And we know that we have to use Snell's law to figure out what the new angle is going to be. Of course, remember we're using the paraxial approximation, so the sine of the angles is roughly equal to the angle itself. Of course, we're working in radians. So in that case, we can re-express theta 2 by dividing both sides by n2, and we get this expression here. Recasting these two equations into the matrix gives us this refraction matrix here, where we have the ratio of the refractive indices down here. And sometimes we use the symbol R as a shorthand for that matrix. If our ray down here, indicated by the vector y1 theta 1, hits a spherical surface, it will refract and change angle. Now, most importantly, the angle that it changes to depends on its y. So in this example, if that ray were to hit here with the same theta 1 but with a different y, then it would be refracted by a different amount because the tangent of that surface is different to the tangent at a different height. So this ray would go more in that direction. Okay, it is relatively straightforward geometry plus a small angle approximation to show that the new angle we get, theta 2, is given by the ratio of the refractive indices times theta 1. But now we have this y-dependent term. And of course, as you'd hope, it also includes the radius of curvature, because that's going to make a difference to how much the light bends. So our spherical surface refraction matrix is recast down here, and we sometimes use the symbol S as a shorthand for it. Now what we can do is set up a system matrix, which is going to be a simple 2x2 matrix which can describe the entire imaging system. Now the key thing to do correctly is that we have to get the matrices in the correct order. So in this case, physically what happens is a ray starts at x is equal to 0. It is translated. We shall use T1 as the matrix that describes that process. It's refracted at that spherical surface, S1. It translates within the lens, T2. It's refracted at the other spherical surface, S2, and then it translates T3 to a particular finished distance away from the lens. To work out the system matrix, we write them in the opposite order. So our first process is here on the right hand side. That's our first translation, and the last translation is here on the left hand side. And then you simply get a computer to calculate it for you. There's also a matrix for a thin lens, which you can look up whenever you look up all your other matrices. In this case, though, we've gone through the calculation of it just because it's a simple example to show you how the system matrix calculations work. So in this case, we're going to start with light actually on the surface of the lens, and it's going to be translated through the lens, then it's going to refract a second time. Now, this is a thin lens, so the thickness here is equal to 0, so we can ignore that translation. So the only thing we have is a spherical surface refraction on one side and a spherical surface refraction on the second side. So you can see that we write our thin lens matrix with the things in the opposite order, so S2 first, then S1. We just fill in the values of the appropriate radii of curvature and refractive indices. Remember, the refractive index out here is 1. And we put in the radii of curvature that we need, plug it all through, and we get this expression here. And now notice that this element of the matrix is basically our lens maker's equation. So we can simplify that to this value here. Now we have an optical system here that does imaging. When it's imaging, it means that we've got an object located here and the rays are coming all from a point. That means that all these rays have to have exactly the same Y1. Because it's an imaging system, all the rays are going to converge on an image, and those rays, they might have different angles, but they will all have exactly the same Y2. So what that means is that the arrival height, Y2, must be independent of the launch angle. So this B has to equal 0 if it is a system that's imaging. Another useful thing that you can get from the system matrix of a system like that is the lateral magnification. That's going to be the A element. So here is the A element here and the B element here. So here are 4 different types of optical systems. This one over here is the imaging system, where we have light coming from one point, ending up at one point. We also mentioned before the telescope system, where we had the infinite conjugates. And you can see in this situation, the ABC matrix gives you 1 over the angular magnification for your A term, and your C term should be 0. The D term will also be angular magnification. So you can check out these different imaging systems, and you can always use the ABCD matrix that you have calculated, your system matrix, and compare it to these systems to be able to quickly figure out what kind of system you have. Alternatively, you might have an unknown in the system. You might know that you have an imaging system, but you don't know what C is like. You don't know what your focal length is. But then in that case, you have C is equal to 1 minus 1 over the focal length, and so you can determine that to be 1 over C. So we've seen already that principal planes are really useful for thick lenses and even compound lenses, and so we can take a really complicated lens system and we can simplify it down to simply 2 principal planes. So we can use the matrix system also to describe the positions of those planes. And so the system that we work out here, that gives us, this will be our system matrix here. We'll find out that the effective focal length of our thick lens is going to be minus 1 over C. Okay, so our back focal length is given by the ratio of the A element and the C element, and so we can actually work out the placement, the distance from the second vertex to H2 using this expression down here. And so we can do a similar kind of analysis to work out that the distance H1 from the first vertex to our first principal plane is given by an expression here. Now, it doesn't matter if you're dealing with 2 thin lenses, 2 thick lenses, 7 thick lenses, anything complicated like that. You'll always have a system matrix that comes down to A, B, C, D. And these equations are always true. They will always give you an effective focal length, a distance to the first principal plane, and a distance to a second principal plane. So in this problem, I've given you the system matrix for the optical system. I've already done that calculation for you. I hope you can remember how to do your matrix multiplication. I want you to have a look at the A, B, C, D elements of that matrix and tell me, is it an imaging system or not? Find out the effective focal length. Find out the front and the back focal distances. Find the distances to the principal planes H1 and H2 and draw a diagram. So we do need to look at one other really important way of focusing light. Now, refraction has its drawbacks. One is chromatic dispersion. That is, you know, the focal length of a lens at one wavelength is going to not be the same as the focal length at another wavelength, because those wavelengths see different refractive indices of light. So when it comes to a mirror, the mirror uses the law that the angle of reflection is equal to the angle of incidence, and is completely independent of wavelength. Refraction also has a problem because it relies on transmission. And transmission outside the visible range is actually rather difficult. For example, in the infrared, a lot of things are opaque. Not only that, but in things like the X-ray region, a lot of things have, in fact, most things have a refractive index of about 1. So making a refractive lens is rather tricky. That's why reflection is very important, particularly in the X-ray, ultraviolet, and infrared regions. So a spherical mirror has similar imaging properties to a spherical refractive surface. And then we can use the same paraxial approximations. The advantage of a mirror is that we don't have any chromatic dispersion. We can actually make it very, very large because the thickness is not an issue as it is with a lens. The disadvantage is that it's going to be really difficult to correct for other aberrations, and we'll be talking about more aberrations next week. The mirror formula very simply can be used, and the way that we write that is 1 over the object distance plus 1 over the image distance is equal to minus 2 over the radius of curvature. We're going to be using the same conventions for the radius of curvature. So if the center is to the right of the surface, there's the center, and therefore there's the surface, then we're going to have the radius is positive. The focal length is measured from the focal point to the vertex, and reflected light now goes from right to left. So this is the incident light and this is the reflected light. So you have to be careful that if we have I as a positive number, then the image is going to be on the left. The remaining mirror properties are so similar to those of lenses and spherical refracting surfaces that we don't really need to mention them again. We're just going to be using the usual paraxial theory. So you should be able to solve problems fairly straightforwardly. We have, in this case, a concave mirror with a certain radius of curvature. We've got an object somewhere in front of it. So the questions you've been given are: find the focal length of the mirror, find the position of the image, and draw a diagram. Now in this problem you'll be doing a simulation of what would happen if you were to use a spoon as a mirror. In part A, you're going to hold the spoon so that the concave side of the bowl is towards you. In the second part, you're going to turn the spoon around and now the convex side is towards you. Now, to solve where the image is located, you need to know what is the focal length of this spoon mirror. Now, that is related, of course, to the radius of curvature, and the important thing to notice in these situations is that the sign of the radius of curvature changes. You've turned the spoon around and therefore the relative positions of the center of curvature and vertex have swapped around. In the graphs down the bottom, I've got in the x-axis the distance of the object from the spoon. So I guess the object in this case is your face and you're looking into the spoon. And I've done a plot of the image distance. In situation A, we're looking into the bowl of the spoon, And you can see that usually we have about 1.2 centimeters is roughly where the image distance lies until we start to get close to the focal length. So this positive sign indicates that this is a real image. So the rays are actually converging on a real point, about 1.2 centimeters away. So if you had something small, you could put it in there and you could see a tiny little image. But also what our eyes do is our eyes make sense of diverging rays. So as these rays continue to diverge, okay, your eye will see that, and your eye will see that as coming from an object that is located just 1.2 centimeters in front of the spoon. So you're going to see an image of yourself just in front of the spoon. The magnification of that image, well, we know that magnification goes with the ratio of the image to object distances. And we can see here that the image distance is going to be rather less than the object distance. So we're going to have a demagnified image. Now, in the second situation, we have a minus 1.2 centimeters is now the distance of our image away from the spoon. So this is a virtual image. So again, the rays look like they're coming from a point 1.2 centimeters on the other side. So when you look at that, you'll see an image of yourself, but it looks like you're behind the spoon now. Again, the magnification will be very much diminished because our image distance of 1.2 centimeters is going to be much less than the object distance, which is the distance of your face from the spoon. The other thing to notice is the sign of the magnification. So in situation A, we have a real image and a real object, so the magnification is negative and it's going to be inverted. So we can also talk about aspherical mirrors, and these are free from spherical aberrations, even when they're very, very large. The only problem is that we get a good image only for a single object distance. They also only have a very small field of view. So anything that is off axis, like over here, is not going to be imaged very well. But for some situations, you have a single object distance. One is the spotlight, where the object is the source of light. In these days, that would be a little LED. And with a telescope, the object distance is also always the same, so that's always infinite. In this case, the parabolic mirror is going to be the way to get the best focus. So I have some examples of parabolic mirrors here. This first one at the top is a radius of 64 meters, and it's the radio telescope antenna. So you can see this distance here is L02, and so all of the rays that come in parallel from whatever astronomical source are all going to be focused in onto this detector here. In the second situation, we have a very large optical mirror which is located down in here. And in that case, the light rays that come from space are then all focused onto this secondary mirror here. We can also look at reflection from a curved mirror using the matrix analysis method, and you can see that we have here, this is the important one on focal length term for the reflection process. If the mirror is flat, well, then the radius of curvature goes to infinity, doesn't it? And in that case, our term down here, our C term, goes to 0. And because I am, among other things, an electron microscopist, I really want to include just one final way of focusing things. In this case, we're going to be focusing electrons which are charged. And so we use the Lorentz force in order to make them move. So if an electron is moving in a certain direction with a certain velocity, then if it has a magnetic field that is operating at some direction at right angles to that, then you twist your hands around and you do the right-handed rule, and what you find is that it will experience a force coming out at right angles to that as well. So in this way, what you can do is you can get an electron which is initially traveling down like this to start to take on a spiral. And if you can see the path of the electrons, you'll see that eventually they are all coming into, they're all converging in on this point here. So it is actually a focusing process that has taken place, even though we've started with electrons all traveling parallel. So how does this work? First of all, let's draw in our electrons. Remember, everyone, that electrons are green. Okay. So what we need to do is not only create a magnetic field with a solenoid. Normally a magnetic field with a solenoid is just parallel, but we need to put a little gap here, so that causes the magnetic field to bend. Remember, our electrons need to feel a magnetic field that is perpendicular to the direction that they're traveling in order to experience a force. So if you can have a look at these magnetic fields here, you can see that this point here, then the magnetic fields there on the edges near the iron pole piece have actually got quite a large horizontal component. Whereas here in the middle, there is no horizontal component at all. So the closer you are to the edge, the higher the horizontal component in the magnetic field. So what does that mean? It means that our electrons, if they come down the center, are not going to feel the magnetic force, the Lorentz force. However, if electrons are coming down close to the edge, they will feel quite a large force, and they will then undergo quite a large spiral and come in to converge. So the further the electrons are from the optical axis, they feel a greater Lorentz force. So that means that electrons outside are going to be bent more. Electrons that are traveling down the middle are not bent at all. And that is, of course, focusing. So here we have the focus. So if you can properly design an electron lens, then it will make all the electrons wobble around and cross the optical axis at the same distance from the lens. So that's your focal length. All electron lenses have a positive focal length. They all cause the electrons to travel towards the optical axis, not diverge. They are also really rubbish compared to optical lenses. They have terrible aberrations. More on that next week.